Hello, my genius geometry students. Today we're going to be discussing 8.4, which is the altitude-hypotenuse theorem. Now our goal today is basically to prove and apply the altitude-hypotenuse theorem and use it to find missing lengths in right triangles. Now first, before we can do this, we have to discuss two things. One, we need to review what a proportion is. And second, we actually have to discuss what a geometric mean is. So, first, a proportion. A proportion is an equation that sets two ratios equal to each other. So if I take this ratio A to B and I set it equal to the ratio C to D, this would be a proportion. Now, in a proportion, we have to know that the cross products are equal. So if I cross multiply that way, BC would be equal to AD. Now with this, the things we're multiplying together actually have names to them in a proportion. Okay, one set of cross products is known as the extremes, and the other cross product is known as the means. So we would actually have what is known as an extreme over a mean in the first ratio, and in the second ratio we would have the mean over the extreme. And if you notice, if I cross multiply one way, that would be the product of the means. If I cross multiply the other way, it would be the product of the extremes. This basically sets us up to approach what we refer to in mathematics as what's called the geometric mean. Okay, this is something that occurs frequently in all types of mathematics, and is basically a type of average that uses the product of the values versus the sum of the values. Our typical arithmetic mean adds the numbers and divides by the number of terms you added, whereas the geometric mean uses the product of the values and then divides by that number. Now, we look at it a little different in this class. We're going to take the geometric mean as being a proportion in which the means are the same. So when we set up our proportion now, we're going to have our extremes as, say, A and B, but we want our means to be the same, such as X and X. And in order to find the geometric mean between two numbers, all we're basically going to do is solve our proportion. Whereas here you'd get X squared equals A times B. And what do I generally do to get rid of the exponent 2? I take the square root, and X equals the square root of A times B. Now, the example below actually asks us to find the geometric mean between the two numbers 4 and 18. Big thing here you have to note, 4 and 18 are going to be our extremes. Okay, we're going to let our variable X be our means. So we would set up our proportion extreme of 4 to the mean of X equals the mean of X to the extreme of 18. And when I cross multiply and solve, I get X squared equals 72. Now, in order to solve for X, I would go ahead and take the square root, and X equals the square root of 72. Now, in our geometry class, we do not like our answers to be in this form. We actually like all of our answers to be in simplified radical form. So what's the largest perfect square that goes into 72? Well, that would be 36 times 2. And if I break that down, the square root of 36 translates to 6 square root 2. So the geometric mean between 4 and 18 is 6 root 2. Now, why is this important? Well, let's go and look at this altitude to the hypotenuse theorem. What is in it? What does it mean? Well, if you look here, we have a right triangle drawn here. And in a right triangle, you have to know that the legs, right, make up the right angle. So we're going to call this one leg 1 and this leg 2. Now the longest side, or the side opposite the right angle, is always known as the hypotenuse. Now what we're going to basically do here is we're actually going to draw in an altitude to the hypotenuse. If you remember, an altitude is a segment that is drawn from a vertex perpendicular to the opposite side. So I'm going to start at vertex B, and I'm going to draw an altitude to the hypotenuse, which means since it's perpendicular, it's going to create right angles here. Now what we're going to do is we're going to name this intersection point, point D. If you look here, 3 additional segments were created. 1, the altitude was. So here, this is the altitude of the right triangle. Second is this segment AD. We are going to refer to this as the one piece of the hypotenuse. We're going to consider DC to be the third piece, and that's going to be another piece of the hypotenuse. Now what happens here is when we draw this altitude, 3 triangles are created. Now what we want to look at is, can we determine if these triangles are similar? Well, what I'm going to do here is I'm going to put an arc in angle A. I'm going to put 2 arcs in angle C. Now, if I could put numbers in here, but I don't want to get too confusing, so I'm basically going to try and say, if I have 1 arc here and 90, okay, this angle would have to have 2 arcs in it. Okay, because that angle would have to be equal to angle C. And if I have 2 arcs here, a 90-degree angle here, this would have to have 1 arc in it. Now, let's look at this. Do I basically have 3 similar triangles here? Yes. I end up with 3 similar triangles by angle. Let's look at the 3 similar triangles. First, if I name the original right triangle, I get triangle ABC. Now, that triangle is going to be similar to triangle ADB. Now, if your head starts spinning, completely understand. Let's take a look at it. Now, in the original triangle, right, we had angle A was 1 arc, angle B was a 90-degree angle, and angle C had the double arcs. Now, in triangle ADB, okay, angle A has 1 arc. You notice how those match up, but the D corresponds to B because B was a right angle. Well, D is a right angle here, and then C and B correspond because they are the 2 angles, or the 2 vertices that have double arcs in it. Okay, so right now I've basically stated this yellow original right triangle similar to this green right triangle, and those are going to be similar to this purple right triangle. Okay, now we do have to match the vertices up here again. So how do we do that? Well, if I take ADB, okay, A has 1 arc. In that purple triangle, which vertex had 1 arc? Well, that would be vertex B. Now, D was the right angle. Therefore, in the purple one, which one vertex had the right angle? D also. And B in the green one had double arcs. Well, in the purple one, which vertex has double arcs? That would be C. Now, these are the 3 triangles that we end up getting similar to each other. Now, due to time, I don't want to make the video too long, but if it helps you out, pull out the 3 triangles independently to try and see them a little more clearly. Okay, but let's take a look at the similarity statements here. Since we've already discussed what similar triangles were and what the similarity statements tell us, what we're going to do is we're going to pull out the first two triangles. We are going to take triangle ABC, similar to triangle ADB. We're going to take a look at all of our ratios of the corresponding sides. So first, if I take the first two, so AB to AD, right, equals the second two, BC to, and we're going to keep everything in alphabetical order, BC to BD. And finally, we're going to take the first and last, which would be AC and AB. Now, what happens here, oops, went a little too high. What happens here is if I take the first and last ratios, alright, I can create a geometric mean here. If I take this ratio, AC to AB equals, if I take this ratio, AB to AD, notice how we end up having a geometric mean here, because AB is the same as AB, so this ends up being a proportion where the means are the same. Now, if I were to cross multiply here, I would get AB squared equals AD times AC. Now, AD times AC, you could also do AC times AD. It doesn't really matter. Now, what does this mean? Well, if I look at AB in this original triangle, okay, let me minimize the ribbon here. And didn't help as much as I wanted to, but if I look at AB in the original right triangle, that ends up being leg 1 squared. Now, AD is what I refer to as the piece of the hypotenuse, but not only is it the piece of the hypotenuse, it's a piece of the hypotenuse nearby that leg 1. So we're going to say piece of the hypotenuse nearby times, what is AC? Well, that ends up being the whole entire hypotenuse. Okay, now this probably still means nothing to you. So what we're going to do is we're just going to continue here. And we're going to actually pull out another set of triangles. Let's take these two triangles. Say triangle ADB, similar to triangle BDC. Now again, we're going to write the ratio of the corresponding sides, which means the first two in each, AD to BD, equals the last two, and remember I'm keeping it in alphabetical order, BD to CD, which is equal to the first and last is AB to BC. Now, notice the first two ratios I have here. If I look at the cross product here, doesn't this end up being a geometric mean? Okay, now that ends up being BD times BD is BD squared equals AD times CD. Now let's look at those segments within the triangle. Now if I look at BD, what does BD represent? Well, isn't BD the altitude? So this is really saying this is the altitude squared times. If I look, AD happens to be a piece of the hypotenuse. And what is CD? Well, CD is also another piece of the hypotenuse. So what's going to happen here is in every right triangle, if you draw an altitude of the hypotenuse, the altitude squared would always be equal to the product of the two pieces of the hypotenuse. Okay, now let's just take, we still have one more set of triangles to look at, and we'll use green for it. We're going to take the first triangle and the last triangle. And I'm actually going to do that up here in the corner. Triangle ABC is similar to triangle BDC. Now, writing the ratio of the corresponding sides again, I get AB to BD equals BC to CD, which equals AC to BC. Okay, now let's look for a geometric mean here. Right away I look at the means and I don't really see any means, but if you notice, one cross product here ends up being the same. Now although you see this as the extremes being the same, if I actually write this ratio first, AC to BC equals, and if I write this one second, BC to CD, notice now how I have a geometric mean. So BC squared equals, let's say this one, let's put CD first, times AC. Now, going back and looking at these segments, BC in the triangle, what is that? Well, that's actually leg 2 squared equals. If I look at CD, again, CD is a piece of the hypotenuse. But isn't that the piece of the hypotenuse nearby? Most definitely. So we're going to say the piece of the hypotenuse nearby, and AC is actually the entire hypotenuse. Now, what does all of this mean? Well, basically we get two valuable formulas. Now, basically the explanation is, if we look at the red area here, what we basically say is the leg of the original right triangle acts as a geometric mean between the piece of the hypotenuse nearby it and the whole hypotenuse. If we look at the blue information, when BDs are a geometric mean, well, BDs represent the altitude, so the altitude acts as a geometric mean between the two pieces of the hypotenuse. And in the green information, we see that leg 2, alright, or segment BC, ends up acting as a geometric mean between the piece of the hypotenuse nearby, which is DC, and the entire hypotenuse. Now again, all of these will always end up happening if you have a right triangle and you draw an altitude to the hypotenuse. Now, how do we use this? Well, basically there's two valuable formulas that come out of this. Okay, first, if we go back up and look at this, the red and the green basically told us that the legs act as a geometric mean between the piece of the hypotenuse nearby and the entire hypotenuse. So one formula we come up with is leg squared, and when we say leg, we are referring to the leg as being the original, or actually let's rephrase that, the leg of the original right triangle. Now, the leg squared is equal to the piece of the hypotenuse nearby times the entire hypotenuse. Okay. Now, another formula that we came up with is when the altitude acted as a geometric mean. Okay, and that formula we came up with is altitude squared equals piece of the hypotenuse times piece of the hypotenuse. So that's the second one that we were able to come up with. Altitude squared equals piece of the hypotenuse times piece of the hypotenuse. So why is this valuable? Well, what it comes down to is, in a typical proportion, we've generally had, if we cross multiply, we want to find one variable. Okay, sometimes it's not easy to find a lot of information. So these formulas limit the number of pieces we need to know in order to find missing information. Okay, so let's put these into place in order to find the value of the variables in the triangle below. Now notice, this here is my original right triangle. Therefore, this is a leg, this is a leg. Now, from there, here is my altitude. If you remember from up above, we're going to call this a piece of the hypotenuse, this a piece of the hypotenuse, and this is the entire hypotenuse. Now, let's start with x. X is a piece of the hypotenuse. And if I look at it, I know the altitude, I know this piece of the hypotenuse, but I'm looking for the other piece of the hypotenuse, x. So, using the formula, altitude squared equals piece of the hypotenuse times piece of the hypotenuse. If I fill this formula out, what is my altitude? Well, that's 6. So 6 squared equals, what's one piece of my hypotenuse? Well, 3 times what's my other piece of the hypotenuse, x. Well, if I go and solve for x, I get 36 equals 3x. So what does x equal? 12. So the length of this piece in the triangle is going to be 12 units long. Now that I have that piece, okay, what would the length of the entire hypotenuse be? Well, what would I do with the 12 and the 3? Well, I would add them together. 12 plus 3 gives you 15. So the entire hypotenuse is 15 units long. But we still have 2 more variables to find. First, let's go and find y. Okay, now what is y in this original right triangle? Y is a leg. So right away, if we're looking for a leg, we are going to use the leg squared equals a piece of the hypotenuse nearby times a whole hypotenuse. So let's take a look at this. To find y, we're going to use leg squared equals the piece of the hypotenuse close by or nearby it times the whole hypotenuse. Now, what's the length of the leg there? Well, that's y. So y squared equals, if I'm looking at y, what is the piece of the hypotenuse nearby it? Well, this is the piece of the hypotenuse nearby. So that's going to be 12 times what's the length of the whole hypotenuse? Well, that is 15. Okay, well, that allows me to go ahead and basically solve for y. So y squared equals 12 times 15 gives you 180. And now, to solve for y, I would take the square root of 180. Now, we basically have to find the largest perfect square that goes into this. Okay, and simplify this radical. We would break this up into the square root of 36 times the square root of 5, which gives you 6 root 5. Now, the nice part about this is y has a length of 6 root 5. Basically, we could have used Pythagorean theorem in this case, but it doesn't always work out that way. Okay? But a lot of times, we don't have enough information to use things such as Pythagorean theorem to find missing sides. So this gives us an advantage to help us find several other pieces, which means we still have to go and find z. So how do we find z? What is z? A leg. So right away, I know I'm going to go and use the leg squared formula. So leg squared equals piece of the hypotenuse nearby times the whole hypotenuse. So looking at this, if I'm at Z, what is the piece of the hypotenuse nearby? Happens to be 3. So leg squared, Z squared, equals piece of the hypotenuse is 3 times the whole hypotenuse is 15. When I go to solve this, Z squared equals 45. Take the square root. Z equals the square root of 45. And that will simplify into the square root of 9 times the square root of 5, which gives you 3 root 5. So basically, this is an introduction to what we're going to be doing tomorrow in class on Monday in order to find missing pieces of a right triangle. This is the altitude to the hypotenuse theorem. Hopefully towards the end you understood why we're doing this, and it makes sense. We will be talking over it in class, so enjoy the rest of your weekend, and I'll see you in class on Monday.